Alright folks, what I'm going to do here is I'm going to go through some example problems trying to calculate current or voltage, resistance, and power looking at simple series and parallel circuits. So I know in the notes we went through some of the equations and talked a little bit about it briefly, but we really didn't get into depth as far as actually trying to solve some of the equations. So what I'm going to do is you guys have a set of series and parallel circuits circuit practice problems that look kind of like this, and I give you this kind of circle of equations, and you won't necessarily be using all of these, but you will be using some of the power equations, and then of course define voltage with current and resistance, or define current with voltage and resistance, or define resistance with voltage and current. Those are all going to be somewhat predominant. So the examples that I do are not the exact same problems that you guys have to solve this week. However, they're going to be like a direct example of problem number 1, problem number 2, problem number 3, and so forth. So if you guys want to follow along to this, it should certainly help you out solving some of the problems. So problem number 1, or example number 1, you guys have a real basic circuit. Looks something like this. They got a voltage source over here. It's got one resistor in it, and they do tell you that there is a certain resistance and a certain voltage. So I'm going to change the values that they give us, but I'm going to still go through and solve them. We're going to say we have a voltage source that's equal to 6 volts, and we're going to say that we have a resistance over here of 12 ohms. And the question is, how much current is running through the circuit? Alright, well, you want to kind of take a look at what you have. We have voltage, we have current, so we know that your V is equal to 6, we know that the resistance is equal to 12, and we're trying to figure out what the current is. Now, listing the variables, just like we do in most physics problems, you want to try to list what you already know, look at what the unknowns are, then you can maybe search around for equations if you need to. That circle that I gave you at the beginning, some of the more common equations again, V equals I times R, resistance equals V over I, and current equals voltage over resistance. Those are going to be the most predominant, and then again we'll talk about power, voltage, and current relationships here at the very end in kind of simple circuits. So when I'm looking at this and I want to try to find I, you gotta go to the circle, and over here they're kind of broken up into quadrants, and the lower left hand quadrant shows current as being power over resistance squared rooted power over voltage, or voltage over resistance. Of course we have voltage and resistance because that's what was given to us. So I equals V over R is the equation that I would go with. And it's nothing more than plugging in the values that we actually have. So if I do that, we got voltage equal to 6 volts, and the resistance equal to 12 ohms. And if you do 6 divided by 12, you're going to get 5 amps. So pretty basic, pretty straightforward. The whole concept or idea here, though, is if you do know the voltage and you know the total resistance, we can figure out the flow or current going through the wire. Now, as we go along, we're going to talk about what happens if you have more than one resistor in a row or in series, or what happens if you have things that are wired in parallel. We're going to kind of get to take a look at those here in the next couple of examples. So, example number 2, this one talks about a circuit that has 2 resistors in it. So it shows resistor 1, it shows resistor 2, it goes back over here, and in the problems that you guys have, again, voltages, resistances might be different. Well, let's just say, for example, we start over here with 25 volt source. Let's say that we have an R1 here and an R2 here, resistance 1, resistance 2. Let's just say that the value for resistor 1 is equal to 2 ohms, and let's say the resistance for the second one is equal to 7 ohms. Then we need to try to figure out, based on the voltage that we have here, 25 volts, what is the current. So our equation, I equals V over R, will still work, but we have to do something with the resistances first. If you want to try to find the total flow going through here, we need to know the total resistance. When resistors or light bulbs or something like that, anything that's going to be drawing resistance or power of some sort, if they're put in series, meaning connected from like tip to tail or tail to end, it's like a single lane road, all the cars, or in this situation all of the electrons, if we're talking about DC power, have to flow through these resistors. So the one in the back can only go as fast as the one in the front. It's kind of like being stuck in a traffic jam. So we need to know what the total resistance is. If it's all on the same road, you literally just add them together. If we want to find the resistance total, I can just take the 2 and add it to the 7 and know that I get a total of 9 ohms. With that being the total resistance, I can go back to my base equation. Current is equal to voltage divided by resistance. And if I can plug in my 25 volts, and I got to divide that by the resistance of 9 ohms, I'll plug that in here and see what we get. I get about 2.78 amps. Now remember, I know this is a higher voltage, but we got a little bit of resistance here also. So if we were to lower the resistance, this would go up. If we were to increase the resistance, then this would go down. For example number 3, we're going to take a look at parallel circuits. And what a parallel circuit is, if you have some sort of a voltage source, you're going to have 2 resistors, almost as if it's got 2 separate paths for them to go. It's going to look something like this. We're going to have some sort of a voltage source over here. They tell us that the first resistor here, R1, is equal to 100 ohms. They're going to tell us resistance 2 over here is equal to 200 ohms. We have a voltage source. In this example, is going to be equal to 12 volts. And we're going to look at a few different questions. First question is going to talk about how much current is flowing through resistor 1, how much current is flowing through resistor 2, and then how much current is actually flowing, through the battery or through the other wires that are feeding those two. So the thing to remember here, when you're dealing with parallel circuits, the voltage across each side of the resistors is always equal to whatever the power source is. So in this situation, it's 12 volts. So I have 12 volts here, 12 volts here, here, and here, all the way across. So if I have more than one path for the electricity to flow, and you have constant voltage on each side, the current through each of those might be different. This one's going to be more than this one because this is a higher resistance. This one's being choked down or slowed up more. The combination of these two is going to be added together and found in the line going in or out of the battery. So there's a couple ways to go about it. If we want to find the the current going across resistor 1, we can look at it like this. You can just do V over R1, and if we want to find the current through resistor 2, we can just do V over R2. Now if we do this, this isn't going to give us the total voltage, this will give us the total current. It'll give us the current through each one of these locations. So if I plug the values in that we got, I got 12 over 100 here. I got 12 over 200 here. Okay? So with that being the case, if we divide those out, we get 0.12 and I get 0.06. So this is the total amount of amps going through each point. So if we look at that, I know again here, this is going to be the 0.2 amps going here. This is going to be the 0.6 amps going through there. If that's the case, if I got 0.12 here and I got 0.06 here, I mean, whether this is, the flow rate of water or something like that, gallons per minute, it doesn't really matter. By the time it comes down here to where there's only a single lane, you could venture to guess that we could just add those two together and the total amps would have to be 0.12 plus 0.06, which is going to give me 0.18 amps. Now, that's not the only way to find the total amperage here. Another thing that we can do is we could find the total resistance, kind of like we did with the series circuit, but finding the equivalent resistance in a parallel circuit is not quite as easy as in series. When they're in series, you can just add them together. I can't add 100 and 200 and say that the total resistance of this is equal to 300. Unfortunately, you got to set it up a little bit differently. If we want the total resistance in a parallel circuit, you're actually kind of adding the inverses of what is there. I can do 1 over R1 plus 1 over R2 will equal 1 over the R total. And you might think, well, that doesn't, who cares? Why don't I just flip the whole thing over? The problem lies, here's our 1 over R1 is 1 over 100, and here's 1 over R2, this is 1 over 200. When you add fractions together, remember this isn't multiplying, we're adding them together. You can only add them if they have common denominators, right? So 1 over 100 plus 1 over 200 doesn't really work. We have to do 2 over 200 plus 1 over 200 to make these fractions addable. And once we've done that, then we have 3 over 200. Now this again is not the total resistance. The total resistance is the inverse of this, because this is 1 over the resistance total. So the resistance total is actually equal to 200 over 3. And if I divide that out, 200 divided by 3, this gives me an equivalent resistance of 66.67 approximately ohms. Now, we talked again about how we got our amperage up here. If we want to try to figure that out again, we can do the total voltage divided by the total resistance. So if we want to look at the current total, I'm going to do the voltage of 12 volts, and I'm going to divide it by our 66.67 ohms, and we should hopefully get something equal to 0.18. So I do 12 divided by 66.67, and I do. I get 0.1799 repeating, so you can see there that we still get the same amount of amps based upon what we got. We'll do another one here. We'll do example number 4. And example number 4, I'm going to get a somewhat of a compound circuit. So the circuit's going to have some series and some parallel circuits involved. So when we start with the battery source, we're going to have one resistor here, we're going to have another resistor here. Then we're going to go down here, we're going to put a couple of resistors in parallel, and then we'll connect it back to the voltage source. So we'll have some sort of voltage source over here. Let's just say, for example, that our voltage source is equal to 12 volts. Let's say our resistance 1, R1 here, is equal to 6 ohms. We're going to say that resistance 2 is equal to 6 ohms. We're going to say that resistor 3, which is right here, is going to be 12 ohms. And we're going to say resistor 4 is equal to 2 ohms. So we got these going through all sorts of different locations. We got series and parallel circuits all combined. One thing that could be helpful if we wanted to try to figure out the total current, like the total current flowing out of here or flowing back into here, we would need to know the total resistance in the complete circuit. And again, if we want to find the total resistance between these two, we can simply add these two together. This is simply going to equal 12 ohms. You just go plus and plus. When we get to this point, again, I can't do 12 plus 2 and get 18, because there's multiple paths for all of this to go. But if I do want to figure this out, I can do 1 over RT equals 1 over 12 plus 1 over 2. And if you're going to add these together, we got to go equivalent fractions. I guess our lowest common denominator here is going to be 12. So this is going to be 1 12th plus 6 12ths. And if I add those together and get 7 12ths, my resistance total here is going to be 12 over 7. And if I divide that out, I'll get the total resistance of the parallel portion of the circuit. So we're going to do 12 divided by 7. This gives me about 1.71 ohms. So if I want the resistance total for the entire circuit, it's going to be the 12 plus the 1.71. This is going to give me 13.71 ohms. Why is that helpful? Because if we want to find the current, maybe in one location, I'll call this current total across the whole thing. I would have to take the total voltage and divide it by the total resistance to get the total current. Our voltage to start with is 12 volts. Our total resistance now is kind of a goofy looking number. 13.71 ohms. And if I divide that out, it will tell me the total flow in and out of the battery. 2.71, so this gives me 0.888 approximately. It's about 8.75. I'm going to stretch it out to this. So that's how many amps we have to work with total. Now we could look at other specific questions that ask us how much current is flowing across these resistors relative to these resistors. Now these are in series or in line, so everything that's coming out of here has to go through here. There's only one path. Everything that's coming out of here, once it gets to this wire, everything has to be going in the same direction or same path also. Where we get a variance on the current is across these two resistors. Now the one thing that's true is this 0.875. Whatever current I get through here or here, the total of those added together have to give me this same value. If these were equal resistances, like if this was 2 and 2, I could just take this value and divide it by 2 and say it's equal across both ones. But we cannot necessarily do that. So there's a couple ways we can go about it. One, we could calculate the voltage drop across these first two resistors in series and see how much voltage is left out of my 12 volts. Because as you go through, every time you cross a resistor, in essence the working voltage that you have on the other side becomes less. I don't have 12 volts from here to here or here to here. If these resistors were gone, sure, I would have 12 volts on each side and we could calculate the current if that need be. So if we're going to go about it in that fashion, I know that this is the same as having, we have this much current and we have that much resistance. If we know current and we know resistance, we should be able to find voltage. Voltage is going to equal current multiplied by resistance. So if I want to go back and try to figure out what is the voltage drop across here, I could do that. I could say I know I got the 0.875 amps and I have a total resistance in that situation there equal to 12. If I multiply this out, multiply the 0.0875 by 12, I get about 10.5 volts. That means from here all the way to here, that's what I'm working with, is 10.5 volts. So what's left over, if I take 10.5 and I subtract it from the 12, I only have 1.5 volts to go across from here to here. To bridge that gap across those two resistors, there's only 1.5 volts left. So if I want to figure out the current in either one of these situations, if I want to figure out the current here across this resistor and the current here going across this resistor, it's V over R. I got 1.5 over 12, and here I got 1.5 over 2. If I divide those out, let's see what we get. 1.5 divided by 12 gives me a small current of 0.125. And over here, if I do 1.5 and I divide it by 2, I get 0.75. You can see, we said before that these two numbers added together have to give me this value. If I do 0.75 plus 0.125, I get 0.875. I can add those two together. I can go back to the 0.875 amps that I had before, which kind of makes sense, because the total flow in versus the total flow out has to be the same. I believe that's known as Kirchhoff's rule. You know, if you had 5 gallons per minute flowing through here, if you break that 5 gallons per minute, if this was water in a hose or whatever, into these two, coming out the other side still has to be 5 gallons per minute, or in this situation, the amperage that we have total. For the next couple of examples, we're going to talk a little bit about power, similar to that. So we'll start out with a real simple circuit. We're going to have a battery source down here, and we're going to connect it to just a simple light bulb here. So the light bulb is going to be glowing bright, and we'll just make it come back around to this direction. So this will be an example for problem number 5. Let's just say, for example, we know the voltage of the battery down here is equal to 9 volts. So let's say we got that. Let's say we know the current running through the wire. Let's say that the current running through this wire is 12 amps. We want to figure out the power consumption of the light bulb, or how many watts is this light bulb. Our equation for power, if you go back and look at the very top, voltage multiplied by current is one of the equations to determine power. Now, power is a given amount of work done in a certain amount of time. And I know we talked about this earlier. Work is force times distance, which will give you a certain amount of energy consumption. If you divided that by a certain amount of time that it was being consumed, that would be your joules per second, and same thing as a watt. So what we're doing here, and there's a conversion to go from joules per second to watts, and watts to horsepower, things like that. But what we're going to do here is just try to figure out the total power. So our power is going to be equal to 9 volts multiplied by the 12 amps. It's 108 watts. That would be the wattage being consumed by the light bulb. And then for example number 6, they give us a little bit larger power source. They tell us that there's a 120 volt power source. They say that there's 3 light bulbs connected together, so they look kind of like this. Light bulb number 1, light bulb number 2, light bulb number 3. They say each of these light bulbs is equal to 60 watts. So they each have a rate of power that they're going to consume. And assuming this is all connected back together, they're asking what is the total current flowing through the wire. Well, let's take a look at what we do know. We do know that the voltage is equal to 120 volts. We know it is equal to all of the bulbs added together. I mean, obviously the more things you connect, the more power they're going to consume. So if we have 60 watts plus 60 watts plus 60 watts, you can multiply it all together and we know we get 180 watts total. If we want to figure out what the current is, we can rearrange our equation. We knew power was voltage multiplied by current, so then the current itself will be power divided by voltage. So let's plug in the values that we got. For power, we got 180 watts. And for voltage, we have 120 volts. And if we divide the 180 by 120, we get 1.5 amps. Alright, so those are just some quick examples. Hopefully they'll help you get through the practice problems that I have assigned to you. Obviously there's a lot of online sources also. You guys can feel free to use those. Online circuit builders, things like that, and other tutorials. So if you guys have any questions, please feel free to give me an email and I'll get back to you guys. Otherwise, have a good day. Thank you very much.